Hello everyone, welcome back to our channel. Today we are going to explore a new topic called Linear Generalized Additive Models. In short form, they are called as Linear GAMs, where GAM represents Generalized Additive Model. We're going to use this linear GAMs for predicting the compressive strength of concrete in this tutorial. This is an end-to-end tutorial, so in this tutorial we will cover everything from scratch to the end, meaning we start from data import, data cleaning, and splitting the data into training and testing sets, machine learning model development, testing the trained model, saving the machine learning model for future use, and we will use the saved model for predicting the compressive strength of concrete on a new data point. Before we dive deep into today's tutorial, I have a small request. Behind every video, we do a lot of hard work to give you the best content. If you like our content, please consider subscribing to our channel. Your subscription means a lot to us and it really motivates us to create more useful tutorials like this. Let's dive into today's tutorial. Before going ahead, let's understand what are linear GAMs actually. So, linear GAMs is a kind of extension to our simple linear regression model. So in simple linear regression model based on least squares, so we use this kind of equation actually, wherein x1, x2 and so on xn are the input features and y is the target feature. What we do is we set some linear relationship between the input feature and the target feature. So x1 is related to y using this equation, y is equals to b0 plus beta 1 times x1 plus this epsilon. This is bias. In this linear regression, every input feature is related to this output feature via some constants. We call these constants as weights. In a generalized GAMs, we replace these terms beta x1, beta x2 with some sort of smooth functions. So these functions can be anything actually. They can be linear equations or a quadratic expressions or a cubic or any generalized spline functions. These functions can be any. So because of this, we are calling this as a generalized model. Generalized means you can reproduce a simple linear regression also with this. So for example, you can look at like this actually. The compressive strength of concrete is related to the input features such as, for example, cement and water like this, beta 1 times cement, beta 2 times water. If you look at the linear GAM, where the output quantity strength is related to the input quantities via some functions, where cement is not multiplied with any constant, or instead we are giving a function that is a variable of the cement quantity like this. F1 of cement represents a function in which cement quantity is the variable and F2 of water like so on. This is the fundamental difference between the linear regression and the linear GAM. One big advantage of using this linear GAMs is this. For example, in your analysis, sometimes some input features are internally related with each other. For example, here cement and water, they are internally related. You can model these interactions very easily in this linear GAMs. This is one big advantage of using this linear GAMs. Here in this tutorial, I am importing these libraries NumPy, Pandas and Matplotlib for data manipulation and data visualization purposes. And here I am using this train, test, split, standard scale and R2 score for various purposes. And these I have imported from sklearn library. And I have imported a new library called pygam. So from this pygam library, I'm importing this linear GAM function and two functions S and TE. S for modeling the spline functions and TE for modeling the interactions. And lastly, I'm importing this joblib library. I'm using this joblib library for data saving and data loading purposes at the end. Once we train the model, we use joblib library to save the trained model, and we use the same joblib library here in this predict notebook to load the saved model and use it for future predictions. So we are using the concrete strength data that was obtained from UCI machine learning repository. Here are the links. You can follow these links and download this data and give it a try. This data consists of overall 1030 samples and 9 columns. These 9 columns represents 9 features, of which first 8 are the input features and the last one is output feature. For people from civil engineering background, they can understand what these parameters are. For people who don't have knowledge about this data, just consider this as some numerical data set which consists of 8 input features, of which one is an integer and remaining 7 are floating points, and the only output feature that we have is a floating point. Just consider it as a numerical data set. That's it. So after I import this data into this pandas data frame, I'm converting this to a numpy array here. I'm doing this just to make this data set compatible with several other libraries. NumPy is very compatible with several libraries. So after that, I'm splitting the entire data set into the input features and the output features. I'm putting this first 8 input features into this variable x and the only output feature into this variable y. When you take the shapes of this, you will see 1030 total samples and 8 input features and 1 output features. So no column is there, it means one column. Here in this cell, I'm doing the main model building and training. So first I'm splitting the data into separate training and testing data sets. Here I'm using train test split function for this data splitting purposes. Here I'm using 20% of the data for testing purpose and the remaining 80% is for training purpose. After I split the data into training and testing sets, here I am doing this scaling operation using this standard scaler. And here are our main linear GAM definition. So here I initiate the main linear GAM model. So what I'm doing is I'm creating this linear GAM with these many parameters. So I'm creating spline functions, 8 spline functions. Each one corresponds to each input feature. 1, 2, 3, 4, 5, 6, 7, 8. And this one is an interaction feature. So wherein I am creating some interaction between the first and the third quantity. 2 represents the third quantity as we start from 0. So what are these 0 and 2? So 0th one is the cement, 0, 1, 2, and the third column is the fly ash. Means I'm creating some interaction between cement and the fly ash because as these are directly related with each other. Fly ash is, we use fly ash as a partial replacement for cement. So that's I'm considering here. Just I'm creating some interaction using this T, and I'm using this fit function to fit the regression model. Once we build the model, I'm using the developed model for predicting the data for this test data set x test scaled. So we repeat this loop until we achieve this R2 score of 0.9. For any model to be statistically good, so 0.85 R2 score is sufficient, but to be on a safer side, I am considering 0.9 R2 score. So once we do the analysis, finally, if it found an R2 score that is greater than 0.9, we terminate this loop and we print training completed, R2 score exceeded 0.9. So it took overall 6 iterations to achieve this R2 score of 0.91. Once we completed the model, here I am plotting the pictures of this predicted versus the actual values of cement quantity versus concrete strength and blast furnace slag versus the concrete strength. So here I am just plotting only 2 variables, and here I am plotting the remaining variables. So if you look at these plots, so the predictions are decent, like the blue dots and the orange dots are mostly close, but there are some situations where we have some less accurate predictions, but overall these are fine actually. And comparing the remaining features like fly ash, water, and super plasticizer coarse aggregate and fine aggregate age, our predictions are nearly decent. Once our visualization and model building is done, here I am saving this developed model into this concrete strength GAM model.pickle, and then the scalar object also I am saving as scalar GAM.pickle. Once we save these files, I'm going to load those saved pickle files into this predict notebook. So here I'm using the same joblib library again to load the machine learning model and the scalar object. Here I have created a new input feature. This input feature is completely new. The data used in this input feature are randomly created, and it is not available in any of the existing trained or testing data sets. So first I'm doing the scaling operation using this loaded scalar GAM. And once the scaling operation is done, I'm using this loaded GAM model for predicting the concrete compressive strength. So the predicted strength is 81.77 MPa, removing this decimal points aside. So our overall compressive strength is 81 MPa. That's it for this tutorial. If you have any questions or recommendations for future videos, please feel free to write in the comment section. We are happy to help you out. If you like our content, please hit the like button and subscribe to our channel. Happy learning. Thank you.